Hello everyone, welcome to Probability and Statistics for Data Science. In this video, we're going to discuss probability spaces. The summary of the video could be that probability spaces encode common sense. The reason why I want to make that very clear from the beginning is that the first time you encounter probability spaces in, a graduate school course can be a little bit intimidating because you see a lot of definitions, sigma algebras, events like axioms, It can be a little bit overwhelming. But I hope to be able to convince you that at the end of the day, all of these mathematical definitions, the only thing that they do is they allow us to implement a very intuitive definition of probability, which is essentially the fraction of times that something happens if we repeat an experiment over and over. Okay, so we'll see what I mean in more detail during the video. But again, don't be afraid of probability spaces. They essentially encode common sense. All right, so the key idea when we define probability and probability spaces is that we want to model uncertain phenomena as experiments that could be repeated over and over and over. This is just an abstraction. We often use this to model phenomena that just happen once. For example, we model the next presidential election in the United States. It's not going to be repeated over and over, but it's a very useful abstraction. All right, so now we're going to define the different elements in a probability space. The sample space is the set of all the possible outcomes of this experiment that we are modeling. And we usually denote it using this letter, a big omega. Let's take a look at some examples. Imagine that we're modeling a six-sided die. What is the sample space? It's the set of 1, 2, 3, 4, 5, 6. Okay, all the possible outcomes that we can get. What if, now something a little bit more difficult, what if we're rolling a die until it lands on a 6? So you want to pause the video and think what the sample space should be. And the answer is actually that it depends. It depends what you're interested in. Because if you're only interested in how many rolls you have to do until you get a 6, then your sample space could just be the number of rolls. And the possible number of rolls in principle is 1, 2, 3, 4 up until infinity, right? Because you could get very unlucky and not get a 6 in many, many rolls. However, you might also be interested in the sequence that happened before we hit on the 6. If that is the case, then you would define another sample space where you would have sequences that end in a 6, like 6, 1, 6, 2, 6, 3, 6, 1, 2, 3, 6, and so on. The set of all those sequences is the sample space. Notice that in both of these cases, these sample spaces are infinite. They contain a countably infinite number of outcomes. An even more complicated example, imagine that we want to model the weather tomorrow in New York City to make it easier in Washington Square Park. So what is our sample space? And the answer here is that it really depends on how we want to model this. For simplicity, let's imagine that you just care about temperature in Washington Square Park. In that case, the outcomes are real values. I'm a little bit out of sync right here. I'm sorry about that. The outcomes are real values, so we can set the sample space to be the reals. Okay, in this case. This time, the sample space is uncountably infinite. You want to get a bit mathematical, but that's not too important. All right, so let's take a look at an overview of the structure of a probability space. We model the phenomenon of interest, as I said, as an experiment that can be repeated over and over and has some mutually exclusive outcomes. I should comment on this mutually exclusive concept. When we perform the experiment, we can only get one outcome. Okay, if we roll a die, we cannot get a 1 and a 2 at the same time. That's what we mean here by mutually exclusive. All right, then what we're going to do is we're going to group those outcomes in sets that we call events. We call them events because it's something that happens. And we're going to assign probabilities to those events. Let's take a look at some examples for the six-sided die. Like an event could be rolling an odd number, 1, 3, or 5, rolling a 4, rolling any number that's also an event, right? Because it's a set of possible events. In this case, it's equal to the sample space. Now let's take a look at, I forgot about this. Let me ask you a question. If we roll a 4, which of these events have happened? Again, pause the video and think about it briefly. Well, for an event to happen, the outcome must be in the event. So if the outcome is 4, this event has happened because 4 is in that event, and this event has happened because 4 is in that event. A has not happened. All right, let's go again to this example where we're rolling a die until we get a 6. Let me ask you a question. How many outcomes are in the event rolling twice to get a 6? Pause the video and think a little bit about it. And this is a little bit of a trick question because it depends on how we have modeled our sample space. If our sample space is the number of times, I'm kind of giving, so remember these two options where we had these two sample spaces, okay? Either the number of rolls until we get a 6 or the actual sequence, okay, until we get a 6. So if we choose this sample space, then the event rolling twice contains just one outcome, right? This outcome, in fact. If we choose this sample space, then the event rolling twice contains 5 outcomes. It contains 1, 6, 2, 6, up to 5, 6. Okay, so it really depends how we define our sample space. This is just to kind of, start conveying the idea that modeling choices can actually be quite important, which is not always obvious when we're providing a mathematical description of probability spaces. Anyways, let me not ramble. Let's go to the example where we're modeling the temperature tomorrow in New York City. So our sample space is the real line. Some possible events could include the temperature is above 30, the temperature is exactly 35, the temperature is some temperature. Okay, so again, sample space is also a valid event. Okay, so now imagine that you measure the temperature and it's 40 degrees. Which of these events have happened? Take a moment to think about it. This one, right? Because 40 is in there. This one does not contain 40, so it has not happened. And this one has happened because it contains 40. In fact, it contains everything. All right, so now let's talk about these probabilities that are assigned to the events. The function that takes an event and gives us the probability is called a probability measure. It quantifies how likely the event is. A function in mathematics that maps a set to a number is called a measure. That's the only reason why we're calling this a measure. So let's go to our intuitive definition of probability. If we repeat an experiment many times, the probability of an event is the number of times the event happens divided by the total number of repetitions. Okay, and this is crucial. Basically, we're going to see that this intuitive definition of probability motivates essentially all of the mathematical definitions related to probability spaces. Okay, so a key question when we're defining a probability space is what events should we assign probabilities to? Okay, what subsets of the sample space do we want to assign probabilities to? And now we're going to basically discuss some rules related to the choice of these events. So let's start with the sample space. This is the event that any outcome occurs. We should include it. We should assign a probability to it. And now let's take a look at what that probability should be. Intuitively, from an intuitive definition, the probability of a certain event is the number of outcomes that are in that event when we repeat the experiment over and over. The thing is that all outcomes are in the sample space. So this is just a ratio between the total number of repetitions and the total number of repetitions. So this should always equal 1 according to our intuitive definition. So the sample space should have probability 1. Now let's take a look at unions and intersections of events. If we assign a probability to two events A and B, we should assign a probability to their union. A or B happen. So these are the outcomes that are either in A or in B. That are in A or in B. It also includes the intersection. And we also should assign a probability to the intersection, which are the outcomes that are in A and B. So now let's take a look at what the probability of a union should be, of a union of events should be when the events are disjoint. Disjoint events don't share any common outcomes. They don't have an intersection. Let's take a look at our intuitive definition. Our intuitive definition says that the probability of this union should be if we repeat again the experiment many times, should be the fraction of outcomes that are in D1 or D2. Okay, we're calling our events, these joint events, D1 and D2. We can actually separate these outcomes because they're disjoint, there are no outcomes that are in both, into the outcomes that are in D1 and the outcomes that are in D2. So we can separate this into a sum of two fractions. And each of those fractions represents the probability of D1 and the probability of D2. So when we have these joint events, from our intuitive definition of probability, the probability of the union should be equal to the sum of the probabilities. And just what we're going to do in a moment is we're going to actually impose this, and this will ensure that our definition of probability measure is consistent with our intuitive definition of probability. Okay, that's where I'm getting at. Okay, but what happens if we're considering a union of non-disjoint events? These events share some common outcomes, so if we apply exactly the same argument again, where we're saying, the union is equal to the outcomes in E1 or E2 when we do all of these repetitions, the fraction of outcomes that end up there, now we cannot separate this into a sum. We have to subtract the outcomes that are both in E1 and E2 because we're counting them twice. But now we can actually separate this into this guy, which is just the probability of E1 intuitively, the probability of E2 intuitively, and we're subtracting the probability of the intersection. So it looks like the probability of the union should be equal to the sum of the probabilities of the individual events minus the probability of the intersection. And this gives us a formula for the probability of the intersection between two events in terms of their individual probabilities and the probability of their union. All right, so if we assign, let's move on with another property that this probability measure should have according to our intuitive definition of probability. If we assign a probability to A, we should also assign a probability to the complement of A, which is the event that A does not happen. This contains all the outcomes that are not in A. What should that probability be? Actually, I'm going to let you think about it for a few seconds. Feel free to pause the video. The key here is to realize two things. The first thing is that, this is the question that you need to think about. Maybe, again, I'm a little bit out of sync with my slides. There's two things that are important to realize here. The first one is that the union of A and its complement is equal to the sample space because each outcome is either in A or not in A. Okay, so that means that the probability of this union is actually equal to the probability of the sample space, which is just equal to 1. The second thing to realize is that A and A complement are disjoint because there cannot be an outcome that is in both. So the probability of this union is equal to the sum of the individual probabilities. And now it's very easy to derive what the probability of the complement is. It's just 1 minus the probability of A. Okay? And again, this is something that we're going to impose just to ensure that the formal definition is consistent with our intuitive definition of probability. And this is enough. We have worked enough on our intuitive definition of probability, and we have derived these properties that a probability measure should satisfy. Now we're ready to define probability spaces mathematically. Okay, so given a sample space, imagine that we have decided what our sample space is. We need to design the collection of events that we're going to assign probabilities to. And we've said that it should include the sample space. It should include the complement of any of the events that are in the collection. We call this a collection, by the way. Collection is just the set of sets, so that we don't say set of sets, or the set of events to which we are going to assign probabilities. So in the collection, we need to have the sample space. We need to have the complement of any event that is also in the collection. And we also need to have the union of any two events that are in the collection. And this third property also extends to countably infinite sequences that are in the collection. Their union should also be in the collection. All right, all of this makes sense. Collections with these properties are called sigma algebras. In fact, if you open a book on probability theory, they just call this thing a sigma algebra. I find sigma algebra not a very intuitive name, and it just kind of scares students. So this is why I've decided to use the word collection instead. Okay, but if you look at other books, this is what a sigma algebra is. Again, it encodes some common sense decisions, in my opinion. So you might be wondering, what about the intersection? What's up with the intersection? Like, we haven't talked about intersections, and that's kind of important to also take them into account. Well, by properties of set theory, you can express an intersection as the complement of the union of the complements of the two events. So by the rules that we have just presented, the intersection should also be in the collection. In fact, arguably, we should just have added that as an extra property, but in mathematics, we like to be as obscure as possible and as terse as possible, so that's why it's not included in the general definition. All right, so let's take a look at an example. We roll a 6-sided die. The sample space is 1, 2, 3, 4, 5, 6. What does the collection of events look like if we want to include events that are associated to each individual roll? Well, essentially we have to, this means that we need to include any possible subset of this guy, because any subset of the sample space can be expressed as a union of these small events. And if those small events are all in the collection, their union should also be in the collection. So basically, if you want to think about what is the number of events that should be included, maybe pause the video and think about it. The number is actually 2 to the 6, because you can think of it in this way. For each of the 6 events, we're choosing whether to include it or not. So then we have to multiply 2 times 2 times 2, 6 times. Notice that we are including an event which is that none of these guys are included. That's called the empty set, and we usually have this notation for it. Okay, it's the complement of the sample space. This is just a mathematical detail. It's not too important. It's not a very interesting event because it's empty and has probability 0 because the probability of the sample space is 1. All right, let me not start rambling. We need to also emphasize that smaller collections can be valid. You can have this sample space like this, and maybe you're only interested in the probability of 2, and you don't care about anything else. So then what's the smallest valid collection that includes this event, the event that only includes 2? Again, feel free to pause the video and think about it. Well, we need to include the sample space. We need to include this empty set that is the complement of the sample space. We want to include 2. We need to include the complement of 2. What's the complement of 2? 1, 3, 4, 5, 6. And actually we're done. You can check that now. If you start taking the unions of all of these guys, you're going to end up with another event in the collection. For example, the union of 2 and its complement is equal to the sample space, and so on. So this is actually a valid collection that is much smaller, and you might want to use it if you're only interested in whether you get a 2 or not. All right, so now we've talked about what events we assign probabilities to. Let's see how we assign probabilities to those events. This is governed by this function that maps the events to their probability, which is called a probability measure. We need the probability to be non-negative. We impose this so that it corresponds to our intuitive definition of probability, where we had a ratio of non-negative numbers, okay? Second, we impose that the probability of the whole sample space is 1. Sample space is 1. Again, we saw that this follows by common sense from our intuitive definition of probability. Third, we impose that if 2 events are disjoint, then the probability of their union should be equal to the sum of their individual probabilities. Again, this follows from the intuitive definition of probability. You can see these rules as trying to implement that intuitive definition of probability. Okay, and this should also hold for countably infinite sequences. That's not too important. All right, so a consequence of the definition is that the probability of the complement is always going to be 1 minus the probability of the event, by exactly the same argument that we mentioned when we talked about the intuitive properties of probability. You will see that this argument completely follows from this if we impose these conditions. What about the probability of a union of events that are not disjoint. This does not follow from the same argument because we only used the intuitive definition of probability to derive this, but we can, let's give it a shot. So let's think of these two events like this, E1 and E2, and we're going to separate them into three parts. The part of E1 that is not in E2, the part their intersection, and the part of E2 that is not in E1. Okay? So I hope it's clear. Let me choose another color. Hope it's clear that we can express E1 union E2 as E1 intersection E2 complement, union E1 intersection E2, union E2 intersection E1 complement. Okay, and these are the sets that I've drawn in different colors. Now these guys are disjoint, so we can express the probability of E1 and E2 as the probability, let me be lazy here and call this A1, A2, and A3. So the probability of the union is equal to the probability of A1 plus the probability of A2. And here I'm going to write the intersection as E1, E2. And now what happens is that when we look at this guy at E1, we see that it's formed by, so the probability, so E1 is equal to E1 intersection E2 complement union E1 intersection E2. So in particular, the probability, let me continue here, the probability of E1 is equal to, wow, my handwriting, oh my God, I'm suffering here, is equal to the probability of A, because this is A. Remember the probability, sorry, the event at the intersection between E1 and the complement of E2, plus the probability of the intersection. Okay, so I promise that I'm getting to the conclusion. By the same argument, the probability of E2 is equal to the probability of, so this is A1, sorry, A2 plus the probability of the intersection. And now when you put all of this together, okay, we showed that the union is P of A1 plus P of A2 plus the intersection, we get it. And here I see that I've made actually a silly mistake, which is that this is actually a minus. Oops. This is actually a minus, okay? That was a little bit too quick. I hope was reasonably clear, because the probability, oh, it's not a minus, it's actually a plus. Wow, I'm a little bit out of it, right? So then the probability of A1 is equal to the probability of E1 minus the intersection. And then when you put that, all of that together, you get this. Okay, this was not my best moment. Let's all, accept this. Wasn't my best explanation, but we're gonna just power through. I hope it was a little bit clear. I think with the picture, you can probably just repeat the argument by yourself. Let's move on. Okay, so there's an analogy with other measures because mass, length, area, and volume, for example, also satisfy some of these properties, right? If you have two different shapes and they're disjoint, then the area of their union is also the sum of the areas. So because of that, we can use Venn diagrams to represent probability spaces and events. So here we use this Venn diagram where the big square corresponds to the sample space. This smaller square corresponds to the event A, the circle corresponds to the event B, and now the area of each of these regions corresponds to the probability of the corresponding event. Is the probability of the corresponding event. So the area of the big square has to be 1, the area of the small square is the probability of A, and then the area of the circle is the probability of B, and the area of this shaded area is the probability of the intersection. And this is a very intuitive way of visualizing probability spaces for very simple examples. but you will see it very often in books on probability. All right, so let's go back to the six-sided die and let's talk a little bit about how we would go about defining a probability measure for that example. Remember that the sample space was 1, 2, 3, 4, 5, 6. The collection that we're interested in is all the possible subsets of the sample space. We don't necessarily need to focus on that collection, but let's focus on that collection because it's probably the most interesting one. We want to be able to define the probability that we roll a 3 or a 4 and so on. Okay, so how do we find the probability measure? At first glance, this might seem a little bit tricky because we have to make sure that all the 64 sets that are in this collection, as we discussed, have to have consistent probabilities that satisfy these conditions that we have imposed on the probability measure. So this feels a little bit tricky. But in fact, there's a relatively simple strategy to do this. We can divide the sample space into the smallest possible components. We'll see what we mean by components in a moment. And then we assign probability to those, and this will allow us to implicitly assign probabilities to all of the possible subsets in a consistent manner. So, okay, what do I mean by components? In order to explain that, I have to explain what a partition is. A partition of a set is a collection of sets, a group of sets. Let's call it a group so that we don't get confused with the word collection that we use for probability spaces. This group of sets have to satisfy two conditions. First, they have to be disjoint. Their intersections are all empty. Second, if you take the union of all those sets, you get the event that you're interested in. So here we're talking about a partition of the sample space. The union of all of these events in the partition has to be equal to the sample space. All right, so now a partition of our sample space is 1, 2, 3, 4, 5, 6, right? Like these individual events, each of which just include one outcome. We're going to assign probabilities to each of the elements of this partition. We're going to call those probabilities theta I. Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, okay? Or theta. I never know if I should say theta or theta. I'm going to go for theta because that's what I've heard more in the United States. Hopefully, that's correct. We're going to, define these thetas to be the probabilities of these individual elements of the partition. Can we choose any thetas we want? Well, no, right? Because these are probabilities. So for starters, they need to be non-negative. Apart from that, we have to realize that the union of all of these guys is equal to the sample space. And that implies that the sum of all the thetas is equal to the probability of the union because all of these guys are disjoint events. And that union is equal to the sample space, so that probability has to be equal to 1. So when we sum all the thetas, they have to equal 1 and they need to be non-negative. It turns out that that's enough. But is this enough to assign consistent probabilities to the rest of the events in our collection? Because remember that the collection actually has 64 events. Well, yes, because what do? For another arbitrary event, what we see is that it's always going to be composed of elements in the partition, because the partition is granular enough, and that's really important. And then we can just basically do the following argument. This is the union of 2, 4, and 6. Okay, this set is the union of those individual elements of the partition. Because they are disjoint, again, we can sum their probabilities to get the probability of their union. And now we can just sum the corresponding thetas to get this probability. And like this, we get consistent probabilities for all of the remaining events in the partition. All right. Okay, so that was actually it. We have shown that a probability space consists of a sample space, which contains all possible outcomes, a collection of events that needs to satisfy some conditions, which I would argue are kind of common sense. Like we include the sample space, we include complements, we include unions and intersections. And then we also define a probability measure that maps each of the events in the collection to their probabilities. And this probability measure has to satisfy some conditions which we impose, but they essentially follow from our intuitive notion of probability, where it's just a fraction of times that something happens when we repeat an experiment over and over and over. So they also make a lot of sense, I would argue, and I hope you agree. Now you might say, okay, this sounds very complicated. So wait a minute. Now I want to, like build a probability space from some data that I have or something. I need to decide on a sample space, decide on a collection, and then assign the probabilities in the collection. And we did this for a 6-sided die, and it was kind of complicated. So imagine that it's, it gets like it's actually a real life example. This sounds a little bit too complicated, and you would be correct. In fact, you would be completely correct. So we never do this in practice. Instead, we use random variables. But before you get very upset at me for wasting your time, we need to define probability spaces so that we are able to define probabilities, which we need to deal with random variables, and also random variables themselves. All right? So don't be mad at me. All right, that's all I got. Thank you very much for your attention.